We're going to continue with our organic chemistry, specifically looking at that C double bond O, specifically what happens when you add an acyl group to another molecule, and that other molecule is a nucleophile. So acylation is the addition of an acyl group to another molecule, a nucleophile. Acylation is carried out using an acyl chloride or an acid anhydride. Let's draw the structure of an acyl chloride now. Here's your acid anhydride structure. I'm sure you can see straight away that we're going to have lots of areas which are electron rich and lots of areas which are electron deficient. So the chlorine and the oxygen of the acyl chlorides are obviously strongly electronegative. So the oxygen and the chlorine will both withdraw electrons from the carbon, rendering it slightly positive. And this slightly positive carbon is therefore easily attacked by nucleophiles. Again, here these oxygens of the acid anhydrides are electronegative, so they withdraw electrons from the carbon, meaning that again, the slightly positive carbon is easily attacked by nucleophiles. Remember that a nucleophile is an electron pair donor. The first mechanism we're going to look at is the nucleophilic addition-elimination reactions using acyl chlorides. Remember, we'll need a nucleophile as well as our acyl chloride. The acyl chloride I'm going to show you is ethanol chloride. So there's our ethanol chloride. Slightly positive carbon, slightly negative oxygen, slightly negative chlorine. Our nucleophile here is water. Has that lone pair that I just told you needs to be present on our nucleophile. That lone pair will attack that slightly positive carbon, causing the breakage of this double bond here. Now, as our nucleophile here is added, that's where the addition comes from, this chlorine is going to be eliminated, hence nucleophilic addition elimination is the name of this mechanism. So here's the addition of that nucleophile. So due to the breakage of this double bond here, this oxygen ends up with a lone pair of electrons and a negative charge. Our nucleophile here, the water, has added itself here, hence nucleophilic addition. This lone pair of electrons on the oxygen is going to move here in order to reform the double bond. And in doing so, this chlorine here will be eliminated, forming a chloride ion, which I'll draw shortly. So finally, we don't want our oxygen left with this positive charge here. So in order to do that, we deprotonate. So the electrons in that bond have gone to that oxygen, effectively neutralizing the positive charge. So to show you our product, by the time all these bonds have been broken and reformed, we'll have a double bond up here from the formation of the bond shown by this curly arrow, and then down here we'll have OH. After all, that chlorine has been eliminated as a chloride ion, which we see here. And then the H plus that's come off here will actually bond to our chloride ion, forming HCl gas. So let's name this. It's simply ethanoic acid. So I'm just going to show that forming as HCl gas, which is kind of problematic because remember that's toxic, which is why, as I'll show you very shortly, we prefer to do this reaction using acid anhydrides because it avoids the production of HCl gas. So in this example, we used water as our nucleophile. What about if we choose ethanol? We're starting with ethanol chloride again. Here's our nucleophile, ethanol. The lone pair is present on the oxygen. That's going to attack at our slightly positive carbon, causing the breakage of this double bond. The oxygen up here will end up with the lone pair. The ethanol will have added itself here. We don't want a negative charge on this oxygen, which means this lone pair will be donated here to form a double bond. Remember, carbon always needs to have 4 bonds, so If we're forming a double bond here, we're going to have to lose something. We're going to use the chlorine. We call this a good leaving group because chloride is a stable ion. So that breaks that bond there. And then we can't keep a positive charge on the oxygen, so we need to deprotonate. So this hydrogen here will leave. Our final product looks like this. We're going to have our carbon double bond oxygen. The chlorine's already left. So let's name everything. This was ethanoyl chloride. Here's ethanol. And here we have an ester, which is ethyl ethanoate. There's the ester linkage. Remember that the alcohol forms the first bit of the ester's name, and in this case the ethanol chloride forms the second part of the ester's name. So to summarise this second equation, we have our acyl chloride reacting with an alcohol to form an ester and hydrogen chloride gas. Let's write the summary equation. There's ethanoyl chloride. Here's ethanol. Our ester is ethyl ethanoate, and we're making hydrogen chloride gas. We're going to work our way through this nucleophilic addition elimination reactions using more examples of nucleophiles. So back in again with ethanoyl chloride. And just keep practicing these until you get used to drawing the mechanisms. I'm going to be using a nucleophile which is a weak base, ammonia. The lone pair exists on the nitrogen. It's going to attack our slightly positive carbon, causing the breakage of that double bond there. Our oxygen gains a lone pair. The chloride ion is our leaving group, so we need to see the breakage of this bond here in order for the chlorine to leave. The ammonia has added itself. Currently it has too many hydrogens, hence why that nitrogen has a positive charge. So we're going to deprotonate by breaking this bond here. To draw a product now, double bond O here, NH2 because we've deprotonated. And then we have left over that chloride ion again. So to name everything, ethanoyl chloride, here's ammonia. And the name of this substance over here is ethanamide. Now, in these solutions which do contain ammonia, what we find in this situation is that it's another ammonia molecule which removes this hydrogen here, forming an NH4 plus ion, and that's going to react with that chloride ion that left to form NH4Cl. Time for another summary equation. So this time we have acyl chlorides react with ammonia to produce amides. And as I was just saying, ammonium chloride will be our second product. So that's example 3. So the nucleophiles we've considered thus far are water, alcohols, ammonia, and now we're going to consider amines. So in our fourth example, we have our ethanoyl chloride again here. We are going to react with an amine. It has a lone pair on that nitrogen. We are going to attack our slightly positive carbon, causing the breakage of that bond here. Redraw everything carefully, showing that lone pair on the oxygen and the negative charge. We know that we're going to have a positive charge on this nitrogen, 2 hydrogens attached, plus our CH3. There's our leaving group, the chlorine. Let's add some curly arrows, showing the formation of that double bond there, the fact that the chlorine's leaving and that we are deprotonating. Final step to draw the product. We have formed what's known as an amide. Now, the amide functional group consists of C double bond O and an NH. So our summary equation now, we've got our acyl chloride reacting with an amine. It's going to form an N-substituted amide. And then because you've got excess of your amine, that's going to cause the deprotonation here. So you'll end up with an extra hydrogen, and that will combine with your chloride ion to form this salt here. Usually you're not asked to draw this comparative mechanism with an acid anhydride, just because obviously the acid anhydride structure is much more complicated. Just to show you this from my revision guide, we're using water here as a nucleophile. The lone pair on the oxygen attacks the slightly positive carbon, causing the breakage of this double bond here. We end up with our negative oxygen, as you would expect, with a lone pair. the electrons move from that lone pair to reform a double bond here. This becomes our leaving group. So that bond there will break, and then obviously we can't keep that oxygen as a positive charge, so we deprotonate, we lose that H+, the electrons are donated here. So our product is quite straightforward here to see. It's going to be ethanoic acid, obviously, but because this is our leaving group, every single time we'll be producing an ethanoate salt. And actually what happens is it reacts with H+ in solution to form another ethanoic acid, in this particular example when water is your nucleophile. So here we are with a summary table. We can see our various nucleophiles, ammonia, amines, alcohols, and water. Here they are reacting with acyl chloride. These were the examples I drew out from a mechanism point of view. And here are the products that we make. We did the water one first of all, which remember made carboxylic acid and HCl gas. Then we moved on to the reaction with an alcohol, which produced an ester and HCl gas. Then we moved on to ammonia, and I said that we produced an amide, and then because of the excess ammonia causing the deprotonation to form an NH4 plus ion, that reacts with the chloride ion that was lost to form ammonium chloride. And then the last most complicated example, we formed an N-substituted amide as well as our NH3Cl, very similar to here. With acid anhydrides, although I didn't draw it out, you can see, look, you're going to produce the same products. So as I just showed you, if we now look at what happens with the acid anhydrides with water, we produce carboxylic acid, and your second product due to the leaving group will be another carboxylic acid. When an alcohol is your nucleophile, you'll produce an ester and a carboxylic acid. For ammonia, you'll produce an amide. And then lastly, your N-substituted amide will be your product when you have an amine nucleophile. So although we drew all those mechanisms involving acyl chlorides, we looked at ethanol chloride time and time again, actually from a laboratory setting, we prefer to use the acid anhydrides such as ethanoic anhydride. The reason for that is because it avoids the production of those HCl gas fumes. So remember I said you get ethanoic acid as a byproduct, which is obviously much safer. In terms of the reactant, ethanoic anhydride is much cheaper, much less corrosive than the comparative acyl chloride. But one advantage of acyl chlorides is they react faster and they produce a purer product, so sometimes they'll still be used in industry. And then a very particular example of this mechanism is used in the manufacture of aspirin, which is a common drug used as a painkiller and blood thinner. It's again made using the nucleophilic addition-elimination reaction. So here you're using an acid anhydride, it's ethanoic anhydride. It's reacting with salicylic acid, which is acting as your nucleophile due to the lone pair of electrons on this oxygen here. So as you can see, this salicylic acid has added itself. We haven't drawn the mechanism, but you can see how this would be your leaving group. Obviously being symmetrical, it doesn't matter which side we pick as our leaving group. So that produces our ethanoic acid, which we said was a safer byproduct, and the rest of the molecule has attached itself here. The reactions of molecules containing the chlorine atom are often affected by other functional groups in the molecule. Consider the reaction of this compound and this compound with ammonia. For the reaction of the first compound with ammonia, name and outline the mechanism and name the organic product. Okay, so this is obviously an acyl chloride. Ammonia is our nucleophile with our lone pair of electrons. Let's start by naming the mechanism. Remember, it's nucleophilic addition-elimination. Okay, so here's our acyl chloride drawn out. Let's label our slightly positive carbon, slightly negative oxygen and chlorine. We'll add ammonia now with its lone pair. It's acting as our nucleophile, which will attack the slightly positive carbon, causing the breakage of that double bond there. To draw the intermediate step, we're going to have a lone pair on that oxygen. Chlorine will become our leaving group. We're going to have a positive charge on that nitrogen plus 3 hydrogens. Time to add more curly arrows. Here's the formation of that double bond. Chlorine becomes our leaving group, and then we deprotonate right here in order to neutralize that positive charge. So we're ready to draw our product. Don't forget to name the organic product. We have 3 carbons, it's an amide, it's propanamide. Name and outline a mechanism for the reaction of this with another acyl chloride, name the amide formed. Nucleophilic addition, elimination. Here's our nucleophile, breaking that double bond. Double bond forms there. Chlorine is our leaving group. Deprotonation occurs. What is the name of this? Well, it's an N-substituted amide, N-ethyl propanamide. So the propanamide bit comes from the 3 carbons here, the N-ethyl comes from here. Butyl ethanoate is used as a solvent in the pharmaceutical industry. Write an equation for the preparation of butyl ethanoate from an acid anhydride and an alcohol. I'm just going to draw this out so you can see it more clearly. Remember, this bit comes from the alcohol, so that will therefore be butanol, butan-1-ol. And then this portion here comes from your acid anhydride, which is going to be the ethanoic anhydride. Don't forget you make ethanoic acid as your byproduct. So I'm just going to write that in terms of how you would put it in your exam. There's butan-1-ol. Here's your acid anhydride. Name and outline a mechanism for the reaction of this acyl chloride, ethanoyl chloride with methanol to form an ester. Nucleophilic addition, elimination. Draw ethanoyl chloride. That lone pair will attack here.